In this video, we're going to talk about some of the important concepts around microstructure and grains as it regards the quantitative assessment of microstructures for line pipe steels. Let's start by talking about the relative size scales of some of the features we're going to be talking about for steel line pipe. We've discussed casting from the liquid to ingots or continuous casting slabs. Those are on the order of a meter or a few meters. And then we move down in size to macrosegregation, where we talked about where the elements go with respect to location in the ingot or in the continuous casting. And then we get down to a smaller size where we're discussing the dendrites, the first grains to grow from the liquid. And then for processed steel, typical grain sizes are on the order of the diameter of a human hair. And now we're in micron sizes, micrometer, where we're at about the size of bacteria or viruses. And that's about the same size as the lamellar spacing between ferrite and cementite lamella in perlite. And then if we discuss the crystalline structure of steel, we're down at the size scale of a nanometer or an angstrom. And then as we talk about atomic structure, we would be down to about 10 to the negative 15th. So we're going to focus a little bit on the crystal structure, and then spend most of our time on the actual grain size or the microstructure. The methods for inspecting different features of steel are different based on the size structure. When you're talking about investigating what's going on at the crystalline structure, tools like X-ray diffraction and transmission electron microscopy have to be used. And then as we work our way up to the size scale of our interest for grains and for microstructure, we will be talking mostly about optical micrographs. That's what's going to be most important for our quantitative assessment of microstructures. Metals are made of crystals. Those crystals are special arrangements of the atoms in close packed structures. Two typical crystal structures are body-centered cubic, where it's called body-centered cubic because there's an atom in the center, and then there's a cubic arrangement of atoms around that body atom. And second kind is face-centered cubic, where there's atoms on each of the faces of the structure of the unit cell, and then there's additional atoms around that face. Those are the two most important crystal structures for steel: body-centered cubic and face-centered cubic. A phase is a physically homogeneous state of matter where the phase has a certain chemical composition and a distinct type of atomic bonding and arrangement of the elements. Within an alloy, there can be two or more different phases present at the same time. The high temperature phase for iron and for most of our line pipe steels will be austenite. The austenite phase has a face-centered cubic microstructure, and the low temperature phase for pure iron is ferrite, and ferrite has a body-centered cubic crystal structure. But most of our line pipe steels will have carbon in excess of 0.018 or 0.022, depending on which phase diagram is being used. And so they will be two-phase combinations that will be present at the same time. They will be ferrite plus carbide. And usually the carbide will be also mixed with ferrite in a constituent called perlite. But before we talk about ferrite and perlite, let's talk about grains and boundaries. Grains are regions made up of all one type of crystal structure and orientation. So if I look at this schematic, I have these lines of atoms representing one crystal structure, and they're all oriented the same. But then when I cross this grain boundary, now it might be the same crystal structure, but it's a different orientation. So here is a image from an electron microscope showing the actual grains and their orientation. And then the grain boundary separates between one orientation and another. So we have grain 1 and grain 2 being distinguished from one another by a different crystal orientation. Now, some grains are big enough even to be seen with the naked eye. This is in Walt Disney World in Orlando, Florida, and I enjoyed when I went to Walt Disney World seeing these cool bronze statues where you can actually see individual grains due to the slow cooling rate. And while we're talking about cooling rate, typically faster cooling leads to smaller grains and slower cooling leads to larger grains. So we would expect in this region of the casting, there might have been faster cooling, and in this region of the casting, there might have been slower cooling, allowing for more growth of the grains. Where do grains come from in the first place? Well, in the liquid phase, there's no crystalline arrangement. The atoms flow freely past each other. However, as you cool a liquid past its freezing point, then it becomes thermodynamically favorable for the solid to form, and solid begins nucleating typically at nucleation sites, and the structure of the growth from that nucleation site is what we call a grain. For metals, it's typically called a dendrite because of the shape of the growth. So if I highlight in red where the nucleation might have occurred, for the schematic in the upper right here, we see several potential nucleation sites, and then growth occurs outward from those into the liquid. And it forms these dendritic shapes because of the energetically favorable regions for the next solid to form. So you get these beautiful, intricate structures that can form, not dissimilar from a snowflake. And here's what a dendritic structure might look like in 2 dimensions, where growth occurred from a mold wall and then went toward the liquid. And then this material was probably quenched in order to freeze these grains, these dendrites in place, so that they could be visualized in this manner. Now, the dendrites don't survive the steel making and pipe making process. And as we've talked about steel making and pipe making, there's many steps that involve heating and deformation of the steel. And that extensive deformation adds hot work and makes it energetically favorable to break down those old grains, the dendrites, and form new grains with more energetically favorable shapes and relationships to one another. So in the upper right-hand corner, we see some typical shapes and relationships of grains to each other in a fractured piece of metal. And that's not that much different from what we can actually observe if we make bubbles. You see in the image on the left, the shapes of the grains are actually similar to the shapes that bubbles can take on. And researchers have found a shape that can be used to simulate the shape of typical grains. That shape is called the tetrachedecahedron. And the interesting thing about this shape is that it can be stacked so that it doesn't leave any void space. So it's useful for simulating a grain structure. And it's also similar to that bubble structure that we saw. And the reason that's energetically favorable, that type of shape, is because it minimizes the surface tension, or the grain boundary energy. So now we're going to watch a simulation that helps us understand what happens when grains nucleate and grow. This simulation was originally for ice nucleation and growth, but the concept is the same for metals. So imagine that you have your ingot at a high temperature. A lot of deformation has gone into the ingot through rolling or some other process to break up the original grains. And so new grains will nucleate at discrete points, and then those grains will grow. They'll grow and they will come into contact with one another, and then the growth becomes competitive. So let's play the simulation. Here's the nuclei. Now a lot of grains are growing. They're running into each other. Now the material has been saturated with grains, so the grains are growing competitively to one another as the temperature goes up. And we're going to stop it here, imagining that this is our final grain structure. In the previous slide, we saw a simulation that showed that heating to high temperatures for long times can cause the growth of large grains. How can grain size affect strength and mechanical properties? So it's well known that smaller grains impart greater strength. So if we look at this plot that has two logarithmic axes, if I have very large grains, 100 microns here, I end up with very soft steel. Now this plot is for pure iron, ferrite, with no other alloying elements or strengthening mechanisms. And if I have very small grains, 0.1 microns or 100 nanometer grains, then I can end up with very strong steel. This is showing for 3 orders of magnitude decrease in the size of the grains, I can get an order of magnitude increase in the amount of strength. Now I've highlighted the region where most of our line pipe steels are in this 35 to 70 KSI region, and also in the around 5 to 50 micrometer region for grain size. So why is the region that I've highlighted actually reflecting a higher strength than the plot does? It's because this plot is for pure iron. If I look at this microstructure, I see this pure iron microstructure with no second phase, no carbide, and there's also no solid solution and strengthening from alloying elements. So there's other strengthening mechanisms that are applied to our line pipe steels to increase the strength above what can be expected only from grain size. And we'll talk a little bit more about those later in this class.